corrections. I told period 1 that we were going to because we were a little bit ahead of them. Yesterday we were talking about what it means for a function to be continuous. What it means for a function to be continuous. We got all the way up to this quickly. We didn't get to examples. We did? We finished all 4?
Oh, we did A.
We did like.
Oh, we did letter A. Okay, so up here we go. Let's review letter A because you guys should know it. The continuity of the function. This function is continuous for all x except, which we show with not equal to
0.
True. What kind of discontinuity exists then at x equals 0? True. But if it is a vertical asymptote, then what kind of discontinuity is that? What category does it put it under? Removable or non-removable?
Non-removable.
Non-removable. Should there be a dash? I never know. There we go. Next one. X squared minus 1 all over x minus 1 is continuous for all x except 1. Remember, the denominator cannot equal 0, therefore x cannot equal 1. True? Now, what is going on at 1? This one is a vertical asymptote because 1 over 0, the discontinuity, that's infinite form. But over here, if I plug in 1, what is that? 0 over 0, which is a whole, and we should know that because we are used to factoring and removing those, right? Hence, removable. Removable. More specifically, a whole, you are totally correct. Letter C. He's hard. Letter D. We'll come back. Letter D. Hopefully you caught on to this from yesterday. Continuous for all. Sign of 0 is 0, though.
Negative.
Sign of negative pi over 2 is negative 1. No big deal. But what is its domain? Does sign have any problems? Nope. Does sign have any problems this way? Nope. He is continuous for all real numbers of x. Now, he is also continuous for all of his domain, but his domain is all real numbers. Whereas he's continuous for all numbers in his domain. Wait, what? Yeah, he's continuous for all numbers in his domain. And what number is not in his domain? There's a discontinuity, right? Technically, every function is continuous except for piecewise. They're funny. But every normal non-piecewise function, absolute value is really piecewise, is continuous everywhere in its domain. All right, the piecewise one. Okay, stink. Hold on. I think in our notes yesterday, when we wrote down the definition of continuous, didn't I write a note about what we should look at whenever we have piecewise functions? It was a quick little squiggle on the side, and I was like, hey, use this for these types and use this for these types. What type of description of continuity should we think of with the piecewise? Did anybody write it down? Go look, definition of continuous. I put little brackets on the outside, didn't I? No. Yeah. Right? Oops. Right here. Go forward. I said these are good with algebraic equations. This is good with a graph or a piecewise. All right, so I'm going to steal that, the thing in the box. I'm going to steal that for us to think through the piecewise one. Ready? Piecewise one. I need the limit as x approaches. Wait, hold on. Imagine this wasn't here. Does x plus 1 have any problems? No. I can plug anything in. There are no discontinuities, no denominator, no radical. So he's fine on his own. How about him? Imagine it was just him, e to the x. Does he have any problems? I don't think so. Doesn't he go forever that way and forever that way? He's fine. So if they're fine individually, where is the only place this piecewise function could have a problem? at 0, because the question is, do they meet or not? However it goes. Do they meet or not? Do they agree or not? That is the big question. How do we figure it out? We say, all right, fine. 0 from below compared to 0 from above. And ask ourselves the question, does that agree with the function at 0? Uh-oh. Sorry, it's H. It's 1. I'm opening the door. I want you guys to look at that piecewise function and think. If I was coming from below 0, which piece would I plug into? And write that function next to that limit. And if I'm coming to 0 from above, which piece am I plugging into? And write that part of the function next to that limit. Ready, set, go. If I'm coming to 0 from below, wait, what's another way of saying below? Less than, right? Oh. And if I'm coming towards 0 from above, another way of saying it is true, or more than, greater than. Maybe that kind of tells me where to look, right? Because 0 from the left, less than 0, which piece is that? Top piece. I'm looking only at the top piece. And if you don't understand that, think of if I was doing a table, I would plug in negative 0.00001, or however many zeros you want. Which one includes negative 0.0001? Only the top, not the bottom. He's greater than 0. Negative 0.001, I'm plugging into this one. What if I'm coming from above 0? 0.001. Above, greater than, I'm plugging into this one. Why do I keep saying plugging in? How do we take limits? Try to plug it in, plug it in. So what do we get for the top one? 0 plus 1 is 1. What do we get for the next one? E to the 0, anything to the 0 is 1. So the limit as I come from the left equals the limit as I come from the right equals my last question, the function value. How do I figure him out? No. Where would I put x equals 0? Which piece? Oh, it's still the first one, and we already checked him out. But that's okay. Let's just make sure. Plug in the 0, add the 1, and say 1. Dun, 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 continuous for all. Because it's fine, x plus 1 was fine, e to the x was fine. The only possible problem was 0. We checked him out, and it's good. So, continuous for all reals. Now, here's the question, though. You think all piecewises are always continuous? How many graphs have we seen that are like, right? They're broken. Why? Piecewises don't match. So we have to be careful. We have to be aware. And to that end, I should take a second to go a little more with piecewise.
I thought you said that piecewise functions are not continuous, and why is this one continuous?
They're only continuous if e to the x looks like, hold on, let me get a graph. Greater than 0. E to the x looks like this, stopping at 0 and not including 0. So e to the x swoops up, right? But I'm only using e to the x here. Here. And then I'm drawing the line. And if the line connects anywhere other than there, it's discontinuous at that in-between point. But the funny thing of x plus 1 is it hits right where the other one stops. So it's okay because they match up. So I could draw this the silly way. I could draw this with my pencil and not have to think about it. But a lot of piecewises don't match up. And those are those like broken graphs that you keep seeing. That's where the problem lies. Noah.
So would it be safe to guess that most piecewise is not continuous?
Most non-carefully made piecewise are not. Okay. I'm going to give you guys a couple examples. I just want you to go ahead and technically this could have been in the limit section, but it's okay. We're talking about piecewises now. And with continuous, we have to be able to take limits, so that's where all this is going on. I'm going to give you guys a couple examples, so go ahead and start writing. I'm not going to solve them, I'm just going to write them. So you guys start writing I'll have the examples up in time for you to write them down, okay? There's an applicable example for the first case. I'm not solving it, you guys are just writing. Just giving myself more room. Finish this in time. AKA finish before I really start talking. Beyond the talking I'm doing right now. Try to think through the example. Basically asking yourself the question, what pieces apply? What pieces apply? How do you use them? Apply. And how do you use them? Here we go. Piecewise functions. The first one should hopefully not be scary. Because where am I approaching? What x value am I approaching in the first example? 3. Now, to approach 3, could I start all the way over at like -10 and eventually work my way up to 3? Yeah. That's not realistic because we don't care about what the driver's doing way over here, way before he decided to meet his friend. We're caring right here, right before the split instant that we're caring about in the sense of what happens at x equals 3. What's going on right before and right after in the sense of approaching from the left and from the right. Meaning, if I was to make a table, because some of you guys, this will help. If I was to make a table, wouldn't 3 be in the middle? Right? And what would be an example of a number that would be just to the right of that if you were using the table to find the limit? 2.99999, right? Whatever, however many you put. How about what's on the other side? 3.00001, right? Here's the long story short. I don't care what's going on at 0, at -10, at -100. I don't care about that. I care about 2.99 and 3.001, right? So here's what's going on. All of these numbers only apply, if 3 is not a separator, only apply to one of the pieces. Because 2.9993, 3.001, or even 2.9 and 3.1 are only able to be found in which piece? First, second, or third? Yeah. All of those numbers only work here. Why? All of those numbers are greater than 2. True? Now some of you are like, well, you could approach from, it doesn't matter. What I'm looking at is this piece because this entails or has all the different values that I would use to approach. I only care about right before. So therefore, all I have to do to solve this limit, I chose my piece. I figured out which piece I'm supposed to do is look at this as what it truly is meant to be. Only that one individual piece. And now how do I find the limit? Plug it in, plug it in. 3 squared is 9, 9 plus 1 is 10. So if x is approaching 3, and if 3 is not a separator, you'll see what's going on when the number you're approaching is a separator. So if 3 is not a separator, I just think about, hey, I'm right before 3, right after 3, and all of that is greater than 2, so I only use that piece. Does that make sense? So give me another example of the limit as x approaches a number that would only apply to one piece. X could be approaching. What would be a number that would put me in this piece? 1 or 1.5 or 1.9 or not 2. Not 2. You'll see why in a second. Not 2. What's one that would be here? The limit as x approaches -1, -10, -100, -3.76. I don't care. All of those would use this piece. Give me one more number that would be here. Limit as x approaches 4.
82.
Or 82.
10 squared. Or 82 trillion.
Oh my goodness. Okay, hold on. Next example. It's different. There's a whole other note. It's a separate case. Still a piecewise function that we're taking the limit of. But now I'm approaching 2. Why is this the problem? Because remember, to take a limit, a two-sided limit, we have to go from below and we have to go from above. And if this is a little too much, some of you are like, uh-oh, I see what's going on. But for the rest of you guys, think of a table. If we're approaching 2, he's in the middle. What would be an example of a number right before?
1.9.
1.99, right? However many nines. What's an example of a number right after? 2.00101, whatever, right? So here's the dilemma. If I need to find this limit, what piece, I'm going to erase the g of x, what piece would I plug in if I need to come from below, meaning 1.99999? Where does that fit? First piece, second piece, or third piece?
Second.
Because 1.999 is less than or equal to 2. Right? Isn't 1.999 less than 2? So I need to plug it in the less than piece. 5x isn't the answer. 5x is what I'm taking the limit of, in the sense of plugging in 2. Look at the next piece. 2 positive, 2 greater than, 2.001. Where does that fit? The third piece. So where do I plug in? And if this is a little too much, 2 greater than, 2 less than, which is ultimately what's going on, which might help you match up with pieces, you can look at the table, 1.99, where would that go? Oh, less than 2. Okay, plug it into 5x. But ultimately, I don't care about plugging in all these nasty things. I can just plug in 2 and say, hey, so as I come from the left in this piece, where am I approaching? 5 times 2 is 10, right? And as I come from the right, where am I approaching? We'll plug in 2. Square root of 2 is square root of 2. Here's the long story short. The limit only exists if the one-sided limits agree. And do they? So therefore the limit does not exist. And because the limit does not exist, it doesn't even matter whether or not it agrees with the function value. If the limit does not exist, is this function continuous at 2? No. Why? Doesn't match up. Doesn't match up. At the bottom, kiddos, it's just a quick little recap of what we just saw. Basically, long story short, whenever you're taking a limit as x approaches c of a piecewise function, and c is a separator. Because otherwise, just plug it into the appropriate piece. But if c is a separator, plug it into both pieces of the function that involve both sides of c, coming from a little bit less than, a little bit greater than. And then compare. And if those two one-sided limits were to agree, what would we say? The limit would exist, right? If this had been something like 3x plus 1, and no, that wouldn't work. 4x, that wouldn't work either. Whatever, 4x plus 2. Plug in 2, 4 times 2 is 8, 8 plus 2 is 10. If that had been 10, the limit exists, and the limit is 10. But did our two limits agree? You guys are quiet all of a sudden. You asleep? Did our two limits agree? No. So therefore, the limit did not exist. Just depends. You got to figure it out. You got to plug into both pieces and check. Now, you might be like, if you look at our section, to be honest, piecewise functions are not a huge emphasis. They're there. But why on earth did I spend this much time on them? AP loves it. AP loves it. We really don't use this page. So this page is just saying like, hey, if something fails, then it doesn't work, right? If something fails, it doesn't work. Let's go for that. All right, here we go. The AP loves it. And this is an example of something that AP might ask. Carla, go ahead.
How do you know when it's approaching the separator and when it's not?
You have to look at the piecewise and look at all the inequalities, not the functions, but the inequalities, and compare what x is approaching with the inequalities. And if that number shows up as one of the boundaries of an inequality, it's a separator. So look at the second example. X was approaching 2, and then look at the function. 2 was in the inequalities. You see it? But look at the one up above. X was approaching 3. Exactly. Jacob.
So if it was like on the first one, if it was instead like x is greater than 3, then you have to separate it.
Yeah. So if 3 was in place of the 2, if 3 was here and 3 was here, we would have had to look at both pieces.
Okay.
But since 3 was fully here, like 2.9 and 3.1, it was fully here, I just used the 1. Okay. All right, let's look at this one. Make it continuous. How? Well, he's a quadratic, so if he was the only one, would he have any problems?
No.
He'd be great. How about him? He's a quadratic. Would he have any problems? No. Polynomials are always continuous. So the only place I could have a problem is, oh, they already told me, -1. So I need to look at, in order to be continuous, coming from -1 below needs to equal coming from -1 above needs to equal f of -1. Why have I left this part blank? Because I want us to choose the correct piece for -1 below. Another way of saying below is less than. Okay, cool. So look at your piecewise function. Which piece is less than? Top one. That's not bad, right? Now, hold on. It needs to be. Oh, we get to make it continuous. Okay, hold on. State it as a fact. It needs to be equal. Okay. Coming towards -1 from above, aka greater than, I'm plugging into. And f of -1, we'll figure him out in a second. Now remember, we don't know who A is. We want to find him. How do I take a limit of something? Plug it in, plug it in. Sat him, you must be equal to. How do I take a limit of something? Plug him in, plug him in. How do I take a function value of something? Wait, at -1 equals -1. Which pieces equals -1? The bottom. Oh, we already did. Okay, fine. Is this really necessary if it's the same thing? It's not always the same thing. I already have it. Why let it? How on earth can they expect me to find A? It's the only variable left, right? So therefore I can say 4 minus a positive 1 equals, well, positive A plus 1. Solve, solve, solve. That's 3. 3 minus 1 is, if A is 2, these two pieces will come together and meet when x equals negative 1. If A was basically anything else, broken. But what did we do? We said, limit from below, plug in the less than. Limit above negative 1, plug into the greater than. And then just solve with algebra. Solve with algebra. We'll do some more examples probably tomorrow. We'll get a warm up in the back of our spiral, but for right now we gotta keep going. Hopefully you guys have this written down. Remember, it's taped this video that's online. Oh, there's another one. Oh, if only we had time. We'll do them in the back of our spiral tomorrow. Alright. Continuity on a closed interval. Continuity on a closed interval. Why am I saying them fancy? I don't know, because I'm bored. But number 2, possibly because he's kind of a technicality. It's a little highfalutin, I suppose, but I'm going to give you an example as you guys write. This isn't a forever card necessarily. It's more of an idea. I just don't want you to be thrown off when you get there in homework. If I was to give you something like, the problem said something like, talk about the continuity of this function or discuss where this function is continuous. Now, we just said a second ago, a few minutes ago, any function is continuous within its domain. So, to be honest, I guess you could put within its domain and box it and be done and kind of have missed half the point of the problem. But you'd be right. But now that I told you that, it's not good enough. Give me the domain. Give me the domain. But if we were to rearrange this problem just a little bit, square both sides, y squared, x squared, move it over, x squared plus y squared is 64. That sounds an awful lot like a circle. But since it's only the positive square root, this is a circle. That's been cut in half. He's only a semicircle. Positive square root, he's above. Negative square root, he's below. He's a semicircle. He's continuous? Yeah. Where? Everywhere in his domain. Huh? He's going to be continuous for all x within. Some of you would be like, ooh, make it open. -6 to 6. No, sorry. Square root of 64 is 8. Sorry. -8 to 8. You say, ooh, make it open. You can't come from the other direction. And if it was a limit as x approaches -8, you'd be right. But if we're talking about continuity, there's actually an exception made for closed intervals that you only have to come from one direction. Above if it's on the left, below if it's on the right. And you can still state that it's continuous on that closed interval, even though there's not a function on the other side. It's just like an exception. It's a technicality. It makes it, I don't know, everything okay. But technically, you could say it's continuous on that entire interval from -8 to 8 that's closed. That's basically what the whole paragraph is saying. You can say a function is continuous on a closed interval coming from only one direction. Meaning, the limit as x approaches the constant only from above has to equal the point, and the limit as x approaches the constant from below has to equal the point. You still can't have a hole. That won't work because it won't equal the point. But you don't have to take a two-sided limit if it's a closed loop. Okay? Because kind of you can think of it as it's not including anything on the other side. All right. Last idea. He's important. He's highlighted. He's important. But I think intermediate value theorem, I think we saw him last year. It's funny, it's like the authors of both of our books are the same. Oh, wait, they are. Means last year compared to this year. Maybe in little ways, but little significant ways. Intermediate value theorem. I need to put in a little e. Do you guys see? Oh, two little e's. I need a little e right. A little e right here. A little e right here. I limited the purpose just a little bit too much when I say it guarantees the existence of zeros. It also guarantees the existence of other specific function values as well. Technically, I'm not going to make you guys put the purpose in, though maybe I should. Oh, that's just never mind. You guys keep writing. You have plenty to write. Yes, excellent job. You guys are getting to exactly where I thought we would get, which is awesome. A little worried for a second we wouldn't get there, but okay. Hey, wait a minute. Wasn't this in the summer packet too? And didn't I ask for the first letter of intermediate and the first letter of value and the first letter of theorem? I think I was getting you ready for its little abbreviation we're going to use this year. This is forever number, I lost track. 5? That sounds right? Forever number 5. Long story short, if I have a function, and if I know that this function is continuous, maybe not everywhere, but continuous on especially a to b, and if I have an a, and if I have a b, and if I have a certain point, how do you change it? And if I have a certain point, and a certain point, and this would be my f of a, because that's the y value, and this would be my f of b. If I couldn't see anything in between, I didn't know anything in between, what could we still definitively say by intermediate value theorem? Since he is a negative y value, and he is a positive y value, and if the function somehow continuously connects this, what has to happen at least once? It crosses this, or that, or that, or that, or that, or that. Do I know for sure it goes up here? Nope, it could be a line. How about down there? Nope, it could be a line. But do I know for sure it has to at least once hit everything in between?
Yes.
I do. Cool kids, homework. Do you want me to say bye? Happy Thursday before Spirit Day. Tomorrow is a Come ready to cheer on your team. No one skip tomorrow. It's like a rite of passage. You have to come. Bye. Nothing else is entertaining to watch.
I just wanted to do it for the grab. Because I didn't want to write. I just felt so tired. I could barely write words. That was like last night. So I just accidentally followed.
Seventh grade? What like level? It's 6.9. Oh.